This is SpaceTime Series 20, Episode 58. Coming up on SpaceTime, the shocking results from a new galaxy evolution study, the new particle that's its own antimatter particle, and Jupiter's great red spot is likely to be a massive heat source. All that and more, including the return of the science report, coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists have been shocked by some surprising results showing that the early universe went through a period of galactic recession shortly after the first galaxies began forming. The unexpected findings reported in the monthly notices of the Royal Astronomical Society contradict prevailing opinions that the very early universe would have been undergoing a period of rapid growth, turning huge clouds of pristine molecular gas into stars and galaxies at rates thousands of times greater than what we see in the local universe today. This was the period of reionization, which began about 400 million years after the Big Bang, some 13.8 billion years ago. It was a time when the cosmic dark ages were ending, the first stars began to emerge, and the universe began to look the way it does today. However, a new computer simulation of galaxy evolution during the first billion years of the universe's existence, created by scientists from Swinburne University and the University of Melbourne, has revealed that these high redshift galaxies were experiencing a kind of cosmic recession. Collectively known as SMORG, the gas simulations featured in this work are part of a larger project known as DRAGONS, which stands for Dark Ages Reionization and Galaxy Formation Observables Numerical Simulation. The new modelling, inspired by economics theory, has revealed that galaxies weren't forming as quickly as they could have. Swinburne University Associate Professor Alan Duffy, who helped create the supercomputer simulation algorithms of the early universe, treated the complex forming galaxies as simple economical models, with raw materials arriving under gravity and being processed into stars. What surprised Duffy and colleagues was that not all the gas that could form stars was being turned into stars. In today's universe, the rate at which new stars are formed is dependent on the amount of molecular gas and dust available for star formation. If the internal consumption rate's too high, then the gas gets used up, and star formation stops until more gas flows in and cools down. Astronomers thought the same process was occurring in the early universe as well. However, this new study shows that this view of the early cosmos is wrong. Duffy says the first galaxies had such a torrent of cold gas flowing into them they simply couldn't keep up. The internal gas consumption can't rise fast enough, with supply outstripping demand. Now, in economics terms, that's a galaxy in recession. Duffy says it's only when the universe expands over billions of years that the rates of material falling into these growing galaxies slows enough to allow the galaxy to find the balance seen today.
The first billion years or so of our universe's history, or at least the simulated universes I've looked in depth at, offer a bit of a paradox. We have a picture of cold, dense gas, lots of potential fuel for stars to form, falling in at a great rate into the galaxies, and naively you would expect them to be booming, just huge amounts of star formation, and ultimately that would lead to the entire universe being lit up, an episode we call the Epoch of Reionization.
Yeah, because when you think about it, is that not only was there so much gas available to make stars and galaxies out of, but also it was all so close together because the universe was physically smaller back then.
Absolutely. This gas was hundreds, thousands of times denser than the universe is today. So things really did happen faster. It did happen at a greater rate. And we kind of expected that to be the case. We thought that in these simulated universes, we'd see the same general form of galaxy growth, which is to say that there's a balance struck between the amount of new stars forming and the amount of gas falling in from outside that galaxy attracted by the gravity to replenish that. For the simple reason, if you form more stars, then you have gas coming in. Eventually you'll run out and you'll form less stars and you'll eventually come into balance. But what we found was the opposite to that. The in-full rate of gas was so extraordinarily high in those early years of galaxies that it actually overwhelmed the galaxy's ability to process that raw material into stars and ultimately to lift its internal demand, the star formation rate, giving us this fairly strange outcome that the galaxies were in a form of recession where the internal demand can't raise or rise to the external supply, which is the definition of a recession, except in this case it lasts for 1 billion years, if not longer. So a fairly substantial, great financial recession.
Are you seeing that model when you actually look that far back in space-time?
Yes, so we've looked in these simulated universes, placing them essentially as if they were as far away from us as it would be in reality, and we've compared them with the telescopes, essentially the Hubble Space Telescope images, and they match all the available data. We're pretty confident that what we see these early galaxies forming in this Dragon simulation series led by Professor Stuart Wythe is actually really what's occurring in those earliest moments of our universe's history, which we are able to see by looking sufficiently deep into the universe with the Hubble Space Telescope, that we see those galaxies as they were all those many billions, about 12.5 billion years ago. The whole thing seems to hang together very well. What you can't do with Hubble is take this kind of careful accountancy approach that we can do with the simulated universe, where we do get to understand or at least see the motion of all the material and count it all and reveal these kind of surprising paradoxes.
This must have come as a huge shock.
It definitely was a bit of a shock. I went and checked my thinking a few times on this. But look, actually, you know what? It turns out that it does make sense from what we call a scaling point of view. And that's simply to say that when you look to the fundamental physics of how material can fall into a galaxy under the force of gravity, that scales much more rapidly with the growth of the universe than does, say, the ability of the galaxy to form stars. So you've got two lines, and essentially they're going to intersect at one point. So really, in a couple of lines of algebra, you can essentially prove that what this enormous computer simulation taking many months on Australia's most powerful supercomputers has given us as an outcome is actually from the most basic fundamental physics of just simply how fast can a galaxy form stars, and how does that change with the universe's density, and how quickly can material fall into a galaxy and how that changes with density. You look at the two lines, you end up getting the answer. But I have to say, it's nice to know that it's some basic physics beneath this paradoxical economic result, but it's also nice to know that the galaxies do eventually come into balance, essentially just a little bit after this ancient period. And essentially we now live in a Milky Way, indeed a universe where, at least for a galaxy's point of view, the economies are balanced. They are in a form of equilibrium. They only form stars at the rate that material falls in to replenish. It's just on this little planet in our Milky Way that we seem to have a bit more trouble getting our economies balanced.
When you pack 10 economists into a room, you'll always get at least 12 different answers. That's got to be food for thought when it comes to anything to do with economics.
Yeah, look, I think I have more trust and more faith, if you can call it that, in the fundamental laws of physics than I do perhaps in economic models. But when it comes to distilling a complex system like a galaxy, economists have had a bit of practice at getting that kind of insight from very complex economic systems here on Earth. So, you know what? I think we can learn a little bit from economic theory and approaching the modeling of these complex galaxies in a way that makes sense from economic theory, but let's not capitalize the laws of economics. I think we want to keep our physical laws very much higher up on the perch.
Explain to me why there is a speed limit on the rate at which stars can form.
So stars can form essentially their fundamental speed limit for forming stars within a galaxy is how fast can coal gas sitting in the galaxy collapse into a star, and that basically, the more dense the material, the faster that can collapse. So we expect star formation rates, so the rates at which galaxies form stars in the early, denser universe, to be faster. That makes sense. But there's not as strong a scaling on that rate as there is on the rate at which material will fall in under gravity from outside the galaxy. It's actually a significantly quicker ability of material to pile into a galaxy than it is for that galaxy to turn that material into stars. So there is this fundamental speed limit, and it's really only apparent in the early universe because it's so dense. It's so enormously smaller, essentially. So all that material is packed in together more closely and hence more densely. But as I said, it really is about the scaling between what the local star formation rate can be and when you go hundreds of thousands of light years away from that galaxy disk, how that material can actually fall in. And it really is just a simple two lines of algebra will tell you that at a certain point in our universe's history that galaxies will be have been out of balance. I think what was really nice about this work is we showed that it's actually in galaxies that are of great interest to us, because these are galaxies that actually light up the universe. They're responsible for, essentially, we call it reionizing all of the hydrogen, turning a universe from dark and cold into one that's hot and ionized, and that's the universe that we live in today. It's very much a field of active research, and it tells us that our intuition based on local galaxies as we see them today might not hold true for these objects, simply because they are out of balance with essentially the economic system, simply because they haven't been able to get that link between the star formation and the rate at which material falls in. And as a result, if you use your local bias view of these galaxies, you might get into trouble.
Does dark matter play a role in your models at all? And if so, do the properties change over cosmic timescales?
We absolutely do have dark matter in these simulated universes. When you create a universe and you don't put dark matter in, you actually don't form galaxies. We need that additional gravity from the dark matter just to get a gravity to form by the present day. So the dark matter is critical. The model we've used is known as a cold dark matter. It's a very standard approach. What I would love to do is to rerun this universe with a different type of dark matter, one perhaps that self-interacts, or one that has a certain amount of internal motion. We call it warm dark matter. And what that will do is actually begin to change the density within the galaxy. It will essentially act, I suspect, and this is always a danger in astronomy where you make a jump, but I suspect that what we'll see is it will actually put the brakes on the forming stars even more dramatically. So I suspect we'll find that this recession perhaps lasts actually even longer into the universe's history than it does already with this cold dark matter model. So it's actually fascinating you've asked that. I'm going to put in a proposal to get some supercomputer time to check this out, because that's actually a really cool idea.
If you can match the results of that to observations, then that would give us a clue as to what dark matter really is. You know, what sort of particles should the people at CERN be looking for?
That's absolutely right. These simulated universes are wonderful laboratories to test the basic laws of physics and the ingredients, and that includes the nature of dark matter. So often we change the properties of the dark matter particle, and the impact is modest, at least for certain ways of looking at a galaxy. So we're always interested in seeing, is there another way I can look at that galaxy that might reveal that telltale hint of actually what that dark matter perhaps is made of, or at least broadly speaking, to direct the particle physics community where to take their experiments, their searches, because right now we're, no pun intended, but we're shooting in the dark here when it comes to dark matter. There really is there's essentially as many dark matter candidates as there are theorists, because everyone pretty much comes up with their own candidate just in the off chance that they're right, in which case they get a Nobel Prize, and it's wonderful. But really we're kind of struggling to get hints on where to be investigating with our detectors here on Earth. So I suspect that, if there's an imprint from the dark matter's nature on these economic processes within a galaxy, that would be a fascinating way to give some handle on where to take this search.
Luckily, Melbourne, which is where you guys are, happens to have a university which is one of the best physics departments in the world.
Oh, look, absolutely. In fact, we're really blessed here in Victoria. There's the University of Melbourne, who have an incredible particle physics team. They have direct access to CERN. There's actually live video feeds from CERN to the Melbourne offices. So you just walk by and you see someone walking by in CERN and you wave to each other. It's very, very surreal. As well as, of course, one of the best astrophysics groups in the Southern Hemisphere, in fact, here at Swinburne. So in such a small location, we have a really unique grouping of experience and world-leading experimentation and observation that can maybe get to the bottom of this, essentially one of the biggest questions in physics, which is what is the nature of dark matter, this stuff that makes up 5 times more than every atom that we can see in the entire visible universe, every star, every planet, every bit of cloud and gas.
And yet doesn't fit in with the standard model of particle physics at all.
It's a complete outlier. If the astronomers hadn't told the science community about dark matter, we would have had no reason to suspect it, much less that it might be so much more dominant than the atoms and the standard model particles. So we live in a fascinating time, and I suspect that to get to the bottom of something so deep and fundamental to our universe will take all of our different approaches, from astrophysics, the observations in astronomy, the simulations of these kind of galaxies, and the particle physics searches, and perhaps together we can answer one of the greatest mysteries in modern science.
Since you're looking at high redshift galaxies, do we know yet which came first, the black hole or the galaxy?
We suspect that in every significant galaxy there is a supermassive black hole at its core, and they're very much linked, the size of the galaxy, for example, and the size of the black hole. What came first? If the black holes are formed from massive stars, exploding, and I mean things that are hundreds of times bigger than our sun. Yeah. Absolutely. The population threes, they can form in a small clump of material that you wouldn't necessarily call a galaxy. It really would be almost an isolated gas cloud, in which case around that black hole you could imagine a galaxy begins to form. So in that case, the black hole would come first. I suspect that the supermassive black holes actually will form within a pre-existing galaxy, or at least something, if you squint, you might imagine this little tiny object, still millions of times bigger than our sun, but small relative to the Milky Way, that galaxy is formed first, and within it, a massive star perhaps has exploded and formed this supermassive black hole. So my money is probably on the galaxy first and then the supermassive black hole, but gee, when you're talking this early in the universe's history, it's a matter of millions of years. Just a few million years will probably change one paradigm to the next. So at least as far as the simulations are concerned, this is an outstanding problem and one that we hope to eventually get to the bottom of. But whether the observations might be able to tell one model from the other, maybe with the James Webb Space Telescope. I'm the eternal optimist, and the technology that we have in the next generation telescopes is so incredible, so exciting that we might get to the bottom of that fundamental question. But for now, I think most theorists would hedge their bet and could come up with very good reasons for why both answers might work.
That's Professor Alan Duffy from Swinburne University. And you're listening to Space Time. I'm Stuart Gary. After an 80-year-long quest, scientists have finally discovered the Majorana fermion, a particle that's its own antiparticle. A report in the journal Science claims the discovery could have some real-life implications for the building of robust quantum computers. Scientists from Stanford University and the University of California made the discovery during a series of lab experiments on exotic materials. While staggeringly important, the discovery wasn't fundamentally surprising because physicists have thought for a while now that Majorana fermions could well arise out of the types of materials used in this experiment. However, by putting together several elements that had never been put together before, and then engineering things so that this new kind of quantum particle could be observed in a clean, robust way, was a real milestone. The particular type of Majorana fermion which the researchers observed is known as a chiral fermion because it moves along a one-dimensional path in just one direction. While the experiments that produced it were extremely difficult to conceive, set up and carry out, the signal produced by the chiral fermion was clear and unambiguous. Back in 1928, physicist Paul Dirac made the stunning prediction that every fundamental particle in the universe has an antiparticle, an identical twin but with opposite charge. And when particles and antiparticles meet, they annihilate each other, releasing gamma-ray energy. It was only a few years later that scientists discovered the first antimatter particle, the positively charged positron, which is the antimatter counterpart to the negatively charged electron. Then, in 1937, physicist Ettore Majorana predicted that fermions, the elemental particles which make up matter and include electrons, muons, taus, neutrinos and quarks, should also include particles which are their own antiparticles. When combined in groups of three and held in place by force particles called gluons, quarks form the protons and neutrons found in the nucleus of atoms. Majorana's prediction applied only to fermions which have no charge, things like neutrons and neutrinos. Now, scientists have since found an antiparticle for the neutron, but they have good reasons to believe that the neutrino could well be its own antiparticle, and there are several experiments now underway to try and find out. But all these experiments are incredibly difficult, and they're not really expected to produce any sort of answer for at least a decade. About 10 years ago, scientists realised that Majorana fermions might also be created in some experiments designed to explore the physics of materials, and so the race was on to make that happen. What they've been looking for are quasi-particles, particle-like excitations which arise out of the collective behaviour of superconducting materials which conduct electricity with 100% efficiency. The process that gives rise to these quasi-particles is akin to the way energy turns into short-lived virtual particles and then back again into energy in the vacuum of space, according to Professor Albert Einstein's famous equation E = mc², or energy equals mass times the speed of light squared. While quasi-particles aren't like the particles found in nature, they'd nevertheless be considered real Majorana fermions. Over the last 5 years, scientists have had some success with this approach, reporting that they've seen promising Majorana fermion signatures in experiments involving superconducting nanowires. The problem is, in those cases, the quasi-particles were bound, pinned to one particular place rather than being able to propagate through space and time. And so it was hard to tell if there were other effects contributing to the signals researchers were seeing. In these latest experiments, the authors stacked thin films of two quantum materials, a superconductor and a magnetic topological insulator, both of which were fitted inside a chilled vacuum chamber, and then sent an electrical current through them. The top film was the superconductor. The bottom was the topological insulator, which conducts current only along its surface and edges and not through the middle. Putting them together created a superconducting topological insulator where electrons move along two edges of the material's surface without resistance. Think of it like cars travelling along a superhighway. The topological insulator was then further tweaked by adding a small amount of magnetic material to it. This made the electrons flow one way along one edge of the surface and the opposite way along the opposite edge. Then the researchers swept a magnet over the stack, making the flow of electrons slow, stop and switch direction. These changes weren't smooth, but took place in abrupt steps, like identical stairs in a staircase. At certain points in this cycle, Majorana quasi-particles would emerge, arising in pairs out of the superconducting layer and travelling along the edges of the topological insulator just as the electrons did. One member of each pair was then deflected out of the path, allowing researchers to easily measure the flow of the individual quasi-particles that kept forging ahead. Like electrons, they would slow, stop and change direction, but in steps that were exactly half as high as the ones the electrons took. And it was these half steps which were the smoking gun evidence the researchers had been looking for. The results of these experiments aren't likely to have any effect on efforts to determine if the neutrino is also its own antiparticle. The quasi-particles observed by the authors are essentially excitations in a material which behaves like Majorana particles. But they're not elementary particles, and they're made in a very artificial way in a specially prepared material. Therefore, it's very unlikely that they'll occur in nature. However, neutrinos are everywhere, and if they are found to be Majorana particles, it would mean nature has not only made these kinds of particles possible, but has literally filled the universe with them. Majorana fermions could be used to construct robust quantum computers which aren't thrown off by environmental noise. That's been one of the big obstacles in quantum computing so far, one of the reasons why we're always saying it's still 20 years off. Since each Majorana is essentially a half subatomic particle, a single qubit of information could be stored in two widely separated Majorana fermions, thereby decreasing the chance that something could perturb them both at once and make them lose the information they're carrying. As to what the new particle would be called, well, the authors are toying with the idea of the term angel particle, in reference to the book and movie Angels and Demons, in which a secret brotherhood plots to blow up the Vatican using a time bomb whose explosive power comes from matter-antimatter annihilation. However, unlike the book and movie, in the quantum world of the Majorana fermion, there are only angels, no demons. You're listening to SpaceTime. I'm Stuart Gary. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook just go to www.facebook.com/Spacetime with Stuart Gary. A new study claims Jupiter's Great Red Spot could be the mysterious heat source behind the planet's surprisingly high upper atmospheric temperatures. Here on Earth, sunlight heats the atmosphere at altitudes well above the surface, for example at 400 kilometres above the planet where the International Space Station orbits. But scientists have been stumped as to why temperatures in Jupiter's upper atmosphere are comparable with those found at Earth. Yet Jupiter's more than 5 times further away from the Sun than where the Earth is. So, if the Sun isn't the Jovian heat source, and it probably isn't, then what is? Scientists from Boston University's Center for Space Physics set out to solve the mystery by mapping temperatures well above Jupiter's cloud tops using observations from Earth. They analysed data from the spectrometer at NASA's Infrared Telescope facility on Mauna Kea in Hawaii, a 3-metre infrared telescope operated for NASA by the University of Hawaii. By observing non-visible infrared light hundreds of kilometres above the gas giant's visible surface, scientists found temperatures to be much higher at specific latitudes and longitudes in Jupiter's southern hemisphere. And those specific locations just happen to correlate with the location of Jupiter's Great Red Spot. The findings, reported in the journal Nature, concludes that the storm in the Great Red Spot is producing two kinds of turbulent energy waves which collide and heat up the upper atmosphere. One of these, gravity waves, acts much like how a guitar string moves when plucked, while the other acoustic waves are compressions of the air, such as sound waves. Heating of the upper atmosphere, some 800 kilometres above the Great Red Spot, is thought to be caused by the combination of these two types of waves crashing, sort of like ocean waves on a beach. So the extremely high temperatures being observed above the storm is the smoking gun of this energy transfer. This tells scientists that planet-wide heating is a plausible explanation to explain why upper atmospheric temperatures are measured hundreds of degrees hotter than can be explained by sunlight alone. A similar effect has also been observed here on Earth above the Andes Mountains, and it's probably taking place in other parts of the solar system and on exoplanets as well. Ever since its discovery in the 17th century, the Great Red Spot has both delighted and mystified scientists. The 16,300 kilometre wide anticyclone is a high-pressure storm larger than the Earth, with wind speeds of over 600 kilometres per hour. I'm Stuart Gary. This is SpaceTime. India has launched a new Earth observation satellite. The Indian Space Research Organisation's PSLV C-38 mission successfully blasted into orbit from the Satish Dhawan Space Centre on the coast of the Bay of Bengal, carrying the 712-kilogram Cartosat-2 spacecraft. Built by the Indian Space Research Organisation, Cartosat-2 is the nation's second locally designed and built cartography satellite. It carries a high-resolution panchromatic camera taking black and white images of the Earth's surface in the visible part of the electromagnetic spectrum. As well as the Cartosat-2 primary payload, the mission also carried 30 small nanosatellites, weighing a total of 243 kilograms. The nanosats came from 15 countries: Austria, Belgium, Chile, the Czech Republic, Finland, France, Germany, Italy, India, Japan, Latvia, Lithuania, Slovakia, the United Kingdom, and the United States. The mission was also the 40th flight for the nation's Polar Satellite Launch Vehicle, or PSLV, and the 17th flight for the PSLV in its beefed-up XL configuration, which includes strap-on solid rocket boosters. You're listening to SpaceTime. I'm Stuart Gary.
Are you ready, eager young space cadets? Oh, sure.
And now on SpaceTime, let's bring back an old friend we haven't heard since the days of Star Stuff on the ABC, namely the Science Report. A new study has found that Aboriginal people first arrived in Australia 65,000 years ago, at least 18,000 years earlier than previously thought. The discovery, reported in the journal Nature, is based on an archaeological dig at an ancient Aboriginal campsite in the Northern Territory's Kakadu National Park. Scientists found artefacts including fireplace remains, stone axes, plant material, grinding stones, spear points and ground ochre used for ceremonial events. The archaeologists then used optically stimulated luminescence techniques to determine how long ago charcoal and sand grains found at the same sedimentary layer as the artefacts were last exposed to sunlight. Ionizing radiation produced by trace amounts of radioactive isotopes gets stored in mineral grains in unstable electron traps which build up over time. Exposure to sunlight affects some types of radiation in those minerals, effectively resetting the electron traps. By collecting the grains at night in light-proof containers and knowing the background radiation levels at the dig site, scientists were able to determine when these grains, and consequently the artefacts that were buried with them, were last exposed to sunlight. The first major migration of modern humans is thought to have left Africa about 70,000 years ago. This new discovery means Australia was one of the first places they reached as they travelled along the shores of the Indian Ocean and across southern Asia. The United States Navy has deployed the world's first operational laser weapon system aboard a warship in the Persian Gulf. The directed energy weapon was installed aboard the USS Penance and is being used as a ship defense system to protect against incoming missiles, aircraft, and surface attacks. The laser can be tuned to up to 30,000 watts, depending on the scale of the threat. As well as quite literally lightning-fast response times, the lasers are also economical, costing only the energy needed to fire them. Infants who have siblings with autism spectrum disorder may have less advanced linguistic and motor skills than siblings of children with neurotypical development. These differences were detectable when the infants were 12 months old and seemed to be sustained until they were at least 3 years of age. Scientists also found the differences in language skills were larger than those in motor skills. The findings are published in the journal Autism Research. A new study claims global warming is likely to double the number of El Niño extreme weather events. A report in the journal Nature Climate Change found that increasing global temperatures by just 1.5 degrees Celsius, well below the 2 degrees allowed under the Paris Agreement, will not only increase extreme El Niño events, but those increases will remain long after the temperatures stop rising. El Niño is a cyclic weather pattern involving warmer than normal ocean water temperatures in the eastern Pacific Ocean and cooler than normal temperatures in the western Pacific. These are powerful enough to affect weather events on a global scale. El Niño usually brings below average spring rainfall across eastern Australia and increased spring and summer temperatures across the southern part of Australia. The Bureau of Meteorology says the 2015-2016 drying pattern in southern eastern Australia was further exacerbated by the warming of the western Indian Ocean, known as a positive Indian Ocean dipole. The new findings follow a recent report in the journal Nature Communications, which showed that the risk of major disruptions to overall Pacific rainfall has already increased. The study says the new El Niño-related impacts will add to the other challenges of climate change, such as rising sea levels, ocean acidification, and ever-increasing temperature extremes. Biologists studying Architeuthis, the giant squid, have determined their giant eyes, the largest in the animal kingdom, are not adapted for the detection of either mates or prey at distance, but rather are best suited for monitoring very large predators like sperm whales at distances exceeding 120 metres and at depths below 600 metres. Known in Norse mythology as the legendary kraken, the giant squid can grow to lengths of over 20 metres. Despite their big eyes, scientists found the optic lobes of giant squid are actually small compared to other squid, while at the same time their cortex cell density was much higher and the cortex itself was both larger and thicker. This means that the optic lobe cortex, the visual information processing area in cephalopods, is well developed in the giant squid compared to other visual parts of the nervous system. That suggests that the brains of giant squid are not evolved proportionally in terms of performing complex tasks compared with shallow water cephalopod species. You can find the full study in the Journal of the Royal Society. And finally for now, a new study indicates that bone strength may be inherited and that its genetic determinants are to some extent shared with bone mineral density. The study, reported in the Journal of Bone and Mineral Research, used high-resolution three-dimensional images to estimate the strength or failure load using a technique called microfinite element analysis. The authors were then able to determine the actual bone strength as an inherited measurement. Knowledge of molecular underlying bone strength is important for predicting an individual's fracture risk and for developing effective prevention and treatment strategies. Future genetic studies of bones can use these measurements to learn more about the genes which are important for skeletal health. I'm Stuart Gary. This is SpaceTime. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more space time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTime with Stuart Gary on Instagram, And on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts or Audio Boom. This has been another quality podcast production from Bytes.com.